Swayam Prabha. Digital India. Educated India.
Okay, so in the last class, so we discussed what's known as thermodynamic potentials, right? So we argued that there are certain thermodynamic variables which are really useful because they only depend upon the initial depend upon the current state of the system, current state in which the system is, right? For example, internal energy, pressure, volume, and so on, right? And later on we also basically introduced many new thermodynamic potentials which can be created from the internal energy itself, right? And the reason they are useful is because, like I said, they are like single valued function. They only depend upon the current parameters of the system, and no matter how we arrive at that particular state, that value is a unique value, right? It's not a path dependent value. And last time, so what we did, so we started with the thermodynamic potential, which is internal energy U, and we used a technique known as Legendre transformation to create many more thermodynamic potentials like enthalpy, the Gibbs free energy, right? The Gibbs potential, the Helmholtz potential F, the Gibbs potential G, and so on, right? So using the Legendre transform. And we also saw that in this particular case for the Helmholtz and Gibbs, this is also known as free energy, and this is a really useful quantity because it goes hand in hand with second law of thermodynamics, in the sense this tells you the direction in which any thermodynamic process is evolving, right? So like we saw that according to second law, any thermodynamic process which is feasible, it has to be true that the total entropy change of the universe has to be greater than or equal to 0, right? And equal to 0 is for the reversible process, but it is greater than 0 for any irreversible process. So similarly, in the last class we saw that this change in free energy for any feasible thermodynamic process has to be negative, right? So if there is a process in which it turns out to be that the free energy change is positive, that process is not really feasible. Okay. And the next step that we will now basically do in today's class is known as Maxwell's relations, and we'll basically derive set of such relationships which are basically just set of equations which relate one thermodynamic potential to the other thermodynamic potential through various thermodynamic variables, right? And the motivation comes from say you are doing some experiment, you are doing some measurement, say one thermodynamic variable is lot more accessible than the other, but we still want to know the value of the other thermodynamic variable. So we are going to derive this set of equations where we can like switch between these thermodynamic quantities very easily, all right. And in order to do that, we have to rely on a very important property of these thermodynamic potentials, the thermodynamic variables, that their differentials are exact differentials or perfect differentials. Okay, I have already discussed about this a little bit, but now I will go into little bit more details. All right. So let us start what's known as exact differentials in thermodynamics. So what do we mean by an exact differential, right? So remember we have been dealing with such indicator diagrams all the time. So, you have pressure on the y axis, volume on the x axis, and if I just draw a point randomly in this plane, we know that this point corresponds to certain pressure and certain volume value, and this state of this system at this value is unique to this point, right. It does not matter how I arrived at this point. I might have arrived at this point through this route or any other route. So, the moment I come here, the property of my system is unique. For example, its internal energy, its pressure, its volume, its temperature, everything is a unique single valued property, all right. So, basically what I am saying is, the state of the system on the indicator diagram can be represented by a single valued function, right. So, what do I mean by that? So, I will give you an example, right. So, say for example, say we consider an ideal gas, right, and we all know what is ideal gas equation, right. So, we write PV equals nRT, right, and here I can very easily see that the temperature of the gas is basically given by PV divided by nR, right. And if I just set this coordinate here, which corresponds to certain pressure value and certain volume value, and if I plug it here, I will always get the same temperature value, right, and it is independent of how I arrive here. So, this is really the property of the system. Okay. So, therefore, in this case T basically corresponds to a state function, basically state function, and the PV equals nRT, which is the ideal gas equation, right. This corresponds to the equation of state, right. So, what is that equation of state which defines the state of a system, state of a function at any particular point, all right. So, therefore, like I just gave you example here. So, in this case I can write my temperature function as a function T, which is now a function of two variables P and V, right. And like we saw, this is PV equals nR, and it is very obvious that this is a single valued function of P and V, all right. Okay. And this property of being it a single valued function also ensures that the differential of T, okay, so the differential of this function T, which is of T, which is dt, is an exact differential, okay, right. And now we will basically try to get into this, right. So, remember I already discussed that heat and work are not really exact differentials, and if you remember I always used a sign d cross on d with W and d cross with Q, right. So, basically I am just trying to get into the mathematical reason why we need such a difference, why we need to distinguish between the d D like this or D with a mark, right. So, or without a mark, okay. So, that is what we are getting into, okay. So, now we will basically see there are two very important properties for any function for its differential to be an exact differential, all right. So, let us get into those properties, okay. So, the property number 1, okay. So, before that, so let us say let us generalize this formulation a little bit. So, let us define a function. So, define a function say z, which is now a function of two variables x and y, okay. So, we have a function which is variable of which has its natural variables as x and y, all right. And the first property for the differential of this function to be exact is that its cyclic integral has to be 0, okay. So, which basically means Okay, so all that means is, so so if I start from this point, right, and I undergo some cycle and I come back here, and if I integrate, so this is x, this is y, if I integrate this, so the integral of this function has to be 0. Okay. So let us see how we can prove it. Okay, so what we will do is, okay, so let me erase it. So say we create a situation where our system is in certain state A and later system is in certain state B, right, and we go from A to B along certain path, which is path number 1, and there is another path we choose where we use path number 2 to transition from A to B, right. So now we can clearly see that in this case we can write our ZB minus ZA, which is the difference between the values of this Z function at B and A. So that is equal to integration of A to B of dz along path 1, right. And similarly we can also write ZB minus ZA to be equal to A to B dz, but now we are going from path 2, right. And now since we are saying that this z is a single valued function, it is it's a state function, right. So it does not matter what path we choose, all it matters is what are the values of this function at A and B, right. So it should be path independent. So therefore so basically for a single valued function, so ZB minus ZA should be equal to each other irrespective of which path we are choosing, right. So the integral evaluated of dz along path 1 has to be equal to the integral A to B along path 2, right. And here I can, what I can do is I can move it to the other side. So this becomes A to B dz1 minus A to B dz along path 2 equal to 0, and I can simply switch the limits of this integral. So dz1, and I can convert this into plus, and this goes from B to A, and this is dz2, and this is equal to 0. And now what I am doing is I am going from A to B along path 1, and then I am coming back from B to A along path 2, and this is nothing but the cyclic integral of this dz, and this is 0, and this is the proof of this, right. So for this function to have an exact integral, its cyclic integral has to be 0, all right. So let us now look at the other important, second important property which is associated with being a perfect differential or exact differential, okay. So and the second property is that, so remember the function that we are dealing with is z, which is a function of x and y, and the property is that its derivative with respect to x and y, okay. So that does not matter how we take the derivative, whether we take the partial derivative with respect to x first and then y first, or y first and then x first, this should be x, they are equal to each other, okay. So this is another very important property of for being a exact differential, okay. And let us see how we can prove it, okay. So let us say again we have this indicator diagram, okay, in the plane of x and y. So say we prepare our system at certain point A and move to a certain point C, okay. So basically what we are saying is, so our ZC, let us assume this is ZA plus small increment of d of z, okay. Okay. So and now let us do okay. So now in order to go from A to C, we can easily take two paths, right. So for simplicity and without loss of generality, we can first choose a path which goes along constant y to a point B Okay, so let us say the point A is corresponds to coordinate x and y, point B corresponds to coordinate x plus dx and y, right. Similarly, point C corresponds to x plus dx, y plus dy, right, and we have coordinate D which is x and y plus dy, all right. Okay. So, and also for this function z of x of y, we can write its differential as follows. So, dz is partial derivative of z with respect to x while keeping y constant times dx plus partial derivative of z with respect to y while keeping x constant times dy. Okay. But now what we can do is we can now look at this indicator diagram, and here we can see that our ZB is equal to ZA times partial derivative of Z computed at A with respect to x while keeping y constant times dx, right. So, all I am doing is I am just adding to evaluate ZB, I am adding ZA plus the partial derivative of this function with respect to x, since we are moving along x and since y is constant, and multiplying by the increment dx, right. So, remember this is dx and this is dy, right. So, very simple. So, and let us call this equation number 1. Okay. And similarly, we can also write on the similar along the similar lines, we can write our ZD equals ZA plus now the partial derivative of Z with respect to y evaluated at point A while keeping x constant, right. Along this path our x is constant times dy, and let us call this equation number 2. Okay. And also similarly, I will just write here. So, our ZC is equal to, now let us move along this path. So, this is ZB plus partial derivative of this function Z evaluated at B with respect to y while keeping x constant times dy, and let me call this equation number 3. Okay. So, now what I will do is I will substitute. Okay. So, substitute ZB from equation 1 to the equation number 3, right. So, I am going to plug in this ZB here and rewriting the form of ZC. Okay. So, you can check your ZC simply becomes ZA plus del ZA divided by del x at constant y dy plus del by del y of this function ZA plus del ZA by del x at constant y times dx, and everything at constant x times dy, all right. And I can now go to next page, and you can see that this simply becomes, okay. So, this is just ZA, so ZA plus del ZA divided by del x at constant y times dx. Sorry, so this should be dx, sorry, so this should be dx. Okay, so this is dx plus so partial derivative of ZA with respect to y, so del ZA by del y at constant x dy plus del double derivative of ZA with respect to del y del x times dx dy. Okay. So, this is what we get. So, del ZA by del y at constant x right at constant x times dy plus the partial derivative of ZA first with respect to x, then with respect to y times dx dy, right. So, first with respect to x, then with respect to y times dx dy, okay. And let us call this equation number 4, and eventually basic, okay, and remember this is zc, right. And what we are doing is we are moving along path a, b and c, right. So, this is the value of zc, okay, evaluated while moving along a path which is a to b to c, right. So, this is evaluated along path a to b to c, okay. And very easily we can also do the same exercise now by moving along a to d to c, okay. And let us do that also. So, similarly also we can write our zc as zd plus, okay. So, zc is zd plus the partial derivative of this function evaluated at d with respect to x while keeping y constant, right. So, zd plus del zd evaluated with respect to with respect to x while keeping y constant times dx, and let us call this equation number 5, okay. And now what we will do is we will substitute, okay. So, we will substitute zd from equation number 2, okay, into equation number 5, right. So, substitute zd from equation 2 to equation 5, and we can check this is what we get. So, zc equals za plus del z a by del y at constant x times dy plus del by del x of za plus del za by del y evaluated at constant x times dy times dx, right. So, and whole thing is at constant y, okay. And I will just expand this. So, this simply becomes za plus del za by del y at constant x times dy plus del za by del x at constant y times dx plus del second derivative evaluated za with respect to del x del y times dy dx, and this is another way to get zc, and let us call this equation number 6, right. And what we have to do now is, so we and this is along path a to d to c, right. So, this is how we are going. So, earlier we evaluated it along a to b to c, then now it is a to d to c, right. So, now we can compare, we can equate equation number 4 and 6, because since z is a single valued function, it does not matter how we arrive here, it should give us the same value, right. So, we can equate these two equations, right. So, basically equating equations 4 and 6, and you can very easily check there are some terms which cancel out. So, za cancels out here, del za by del x dx with cancels here, this term cancels here, and all we are left with is the last term, right. So, all we end up is del square za by del, so del y del x, right, del y del x times dx dy equals del square za by del x del y times dy dx, right. So, dy dx, okay, and these two cancel out, and finally we end up with the expression that we were trying to prove, right. So, second partial derivative of z with respect to y and x is equal to del x del y, and this is what we were trying to prove, okay. For z to be a perfect exact differential, this is another property which must be true, okay. Okay. So, now what we will do is another two more theorems which will be required to derive Maxwell's equations, okay. And the next two things that we will do is they are known as reciprocity and reciprocal theorems. Okay. So, reciprocity and reciprocal theorems. Okay. So, now let us say remember we started with a function z which is a function of x and y, and since we can also rewrite this function in a different way, right. So, since z is a function of x and y, we can also rewrite this function in such a way that we can write x as a function of two natural variables y and z, right. So, this is similar to like how I can express temperature as PV by NR, but I can also define my pressure as nRT by V, right, on another indicator diagram which is in the plane of T and V, right. And similarly, I can also write V as nRT by P and so on, right. So, I can convert these functions into one another, right. So, if now say we have these two functions, right. So, so we can write the differentials as follows. So, dz is del z by del x while keeping y constant times dx plus del z by del y while keeping x constant times dy. Similarly, from the second equation, second function, I can write dx as del x by del y while keeping z constant times dy plus del x by del z while keeping y constant times dz. Okay. And what we will do is, so substitute dx from here into dz. Okay. Substitute dx into equation for dz. Okay. So, I am just going to substitute dx here. Okay. So, if we do that, we can write okay, or we can do the other way, right. So, we can substitute dz here, okay, it does not matter. So, our dx becomes okay. So, what I am doing, substitute dz into equation for dx, okay, it does not matter actually. Okay. So, if we do that, we can write our dx as, so dx becomes del x by del y at constant z. Okay. So, del x by del y at constant z times dy plus del x by del z at constant y times del z by del x at constant y times dx, right, times dx plus del z by del y at constant x times dy, all right. And so, we are just going to simplify this. So, this becomes del x by del y at constant z times dy plus del x by del z at constant y times del z by del x at constant y times dx plus del x by del z at constant y times del z by del y at constant x times dy. Okay. And remember, our left hand side is dx. So, next thing that we will do is we will just rewrite in a more useful way as follows. So, this is del x by del y at constant z plus I am separating the terms containing dy and dx. So, del x by del z at constant y times del z by del y at constant x, and this is times dy plus del x by del z at constant y del z by del x at constant y times dx. Okay. So now what we are saying is our dx, the differential of the parameter x is equal to this term plus something which is multiplied by dx, right, and these two terms have to be equal to each other, right. For this to be true, the coefficient of this first term has to be 0 and coefficient of this second term has to be equal to 1 for dx to be equal to dx, okay, and that's the end of it, right. So since dx equals dx, right, on both left hand side and right hand side, so we can see del x by del y at constant z plus del x by del z at constant y times del z by del y at constant x equal to 0, okay. And I can actually rewrite it in a simpler manner. So, this basically becomes del x by del z at constant y times del z by del y at constant x equals negative of del x by del y at constant z, okay. And since these are all well defined function, these slopes never diverge. So, these are the underlying assumptions that we go into it, right. It's a well defined continuous non diverging function at any point, okay. So, I can always take inverse of this, right. So, I can always write it as inverse of del y by del x, okay. I mean, okay. So, maybe okay. So, before I do that, okay. So, maybe it's actually useful if I go to the second quantity first, right. So, this is the first condition, right, and the second condition, this tells us that del x by del z at constant y equals 1 by del z by del x at constant y, right. So, this is exactly what I just said, right. So, I can always take inverse of this slope, right, and they are both well defined, and in fact this is already known as reciprocal theorem, okay. So, this is known as reciprocal theorem, and similarly I will now get into this. So, I can rewrite this as del y by del x by del z at constant y times del z by del y at constant x equals minus del x by del y at constant z, right. And now I can use the reciprocal theorem and move it to the left side by taking an inverse, right. So, this can be just simply rewritten as so del x by del z at constant y times del z by del y at constant x times, so del y by del x at constant z. So, del y by del x at constant z, and this is minus 1, okay. And again I can now use the reciprocal theorem any number of times essentially, and I can write it in a more systematic manner, right. So, I can take inverse of this and I can take inverse of this again, right. So, this I can very simply write del x by del y at constant z times del y by del z at constant x times del z by del x at constant y is also minus 1, right. So, essentially what I have done is I have just taken this to the other side and taken the inverse, okay. And so, this is like x y z and x y z, right. So, there is this cyclic symmetry in this relationship, and this relationship is known as reciprocity theorem. Okay, and all these theorems will be useful once we do some once we apply. So, we will see we will apply these theorems and these ideas to certain problems. Okay. All right. So, I have talked a lot about what does it mean to be an exact differential, right. And remember I also mentioned that heat and work are not exact differentials, right. So, let us try to understand what do we mean by that. Okay. So, basically examples of not being an exact differentials, right. So, examples of inexact differentials, okay, inexact or inexact imperfect differentials, okay. So, both these terms are used, okay. So, like I said, the differential of work and differential of heat are not exact, that is why we denote them with a parameter with a cross sign on the D, right. And let us see how that looks, right. So, why is that the case, okay. So, now let us go into the indicator diagram of P and V. So, let us just take the example of W, but same thing can be done applied to heat as well, okay. So, say we go from point A to point B, right, and say we go first we go along okay, so maybe so say first we go along path red, let us call it 1, and in the second go we use the route 2, right. Okay, and since the dW is defined as minus of PdV, right. Similarly, we know that the differential of heat is defined as TdS, okay, but I am doing this for the work, okay. So, what is the value of this differential evaluated along path 1, okay, and that is basically negative of P of dV going from A to B along path 1, and basically what this is this is area, maybe I can use the red color. So, area under curve 1, right. So, this is what it represents. So, right. So, if we trace out the path number 1, then the work, then the integral of PdV from A to B evaluated along 1 is basically area under the red curve, right. And similarly, we can see that the differential of work evaluated along path 2 is negative of A to B of PdV evaluated now along path 2, and this is basically area under curve 2, right, and this is what this area is, right. And we can very easily now check that clearly the area under the curve 1 and curve 2 is not same, right. In fact, there is a difference between these two areas, which is exactly the area area spanned by these two area between these two curves, right. So, clearly the dV1 evaluated along path 1 is not equal to dW2 evaluated along path 2, or we can write. So, dW 1 minus dW2 is not 0, or its cyclic integral is also not 0, right. So, therefore, dW is an inexact differential, inexact, right, because if we trace out two different paths, we always do net work on the system, right. Similarly, if we do this exercise for the heat, right. So, then we have to plot this thing in the plane of T and S, and the area under those two curves will be the heat generated, right. So, this is why we should be very careful when using the differentials of work and heat, and that is why we always represent them with a cross mark on the symbol D, okay. So, that is a very important difference that you should always appreciate. So, now let us transition to what is known as Maxwell's relationships, okay. So, Maxwell's relations or relationships, all right. So, like I said, these are set of equations which are always useful if we want to switch between one variable and other variable and so on, okay. So, let us see. So, let us start with the first function, which is basically the first thermodynamic potential, which is the internal energy, right. So, internal energy which is u, right, and we know from first law of thermodynamics that its differential is basically TdS minus PdV, right. And you can see that natural variables or maybe I can just, so here we can see that the u is a function of two natural variables, which is S and V, right. So, this is a function of two variables S and V, all right, and therefore, from here we can see that the temperature is nothing but partial derivative of internal energy with respect to entropy while keeping volume constant, and the pressure is negative of partial derivative of internal energy with respect to volume while keeping entropy constant, right. And since we already know u is a thermodynamic potential, it is a state function, so its differential is a perfect or exact differential, right. So, since du is an exact differential, right. So, we can write, so its partial derivative with respect to first with respect to S and then with respect to V is equal to V and S, right. And here we can basically just split it. So, del by del S of del u by del V evaluated at constant S equals del by del V of del u by del S evaluated at constant V, right. And what is, now we can substitute these values here. So, del u by del V sorry, this should be sorry. So, del u by del V evaluated at constant S is minus P. So, this is del by del S of minus P, and this whole thing evaluated at constant volume, right, is equal to del by del V of del u by del S at constant V, which is T, and this thing evaluated at constant entropy, and that's our first relationship, right. So, this is negative of del P by del S at constant V equals del T by del V at constant S, okay. And this is our first Maxwell relationship, first Maxwell's relationship, okay. So, this is by using the internal energy, right. So, now let us move on to the second thermodynamic potential, which is enthalpy, right. And remember, we defined enthalpy from internal energy using a Legendre transform, which looks as follows. So, we defined our enthalpy function as internal energy plus P times V, right, and its differential we can write as dH equals du plus PdV plus VdP, right, and we can substitute for du. So, this is TdS minus PdV plus PdV plus VdP, right, and these two cancel out and we get TdS plus VdP dH, and here we can see that H is a function of two variables S and P, right, and clearly we can write our temperature as partial derivative of enthalpy with respect to entropy at constant pressure, and our volume is partial derivative of enthalpy with respect to pressure at constant entropy, right. And again, by using the property that enthalpy is a thermodynamic potential, it is also a state function. So, its partial derivative with respect to its two natural variable, the order does not matter, right. So, again del square H, again let us use this relationship del square H by del S del P equals by del P del S, right. And again we can basically just substitute this here. So, we can do del S del by del S of del H by del P, right, at constant entropy equals del by del P of del H by del S at constant pressure, and this is at constant constant pressure, and this entire thing is at constant entropy, right. and now I can substitute. So, del H by del P at constant entropy is V. So, this becomes del V by del S evaluated at constant pressure equals del H by del S is T. So, del T by del P at constant entropy, okay, and this is the second relationship, second Maxwell relationship. Okay, so similarly in the same repetitive manner we can derive two more. So, the third one is Helmholtz potential or free energy or function, right, potential, and this is F, right, and again we did the Legendre transform, which is u minus Ts, and here we can write our differential as follows. So, df is du minus Tds minus Sdt, okay. Again, so this is Tds minus Pdv, I am substituting for du minus Tds minus Sdt, and Tds cancels out. So, we have minus Pdv minus Sdt, and this df, and now f is a function of two natural variables, which is v and t, okay. So, again, so del square f by del v del t equals del square f by del t del v, right, and here we can check. So, this is del by del v of del f by, okay. So, again from here we can write pressure as negative of partial derivative of f with respect to volume at constant temperature, and entropy is negative of partial derivative of f with respect to temperature at constant volume, right. So, therefore, so del so from here we can see we get del by del v of del f by del t, and what is del f by del t at constant volume? This is minus s. So, I can just skip one step. So, this is del s by del v, but now evaluated at constant temperature equals del by del t of del f by del v, which is p, right. So, there is another minus sign. So, del by del t of p, and this is evaluated at constant volume, right, and we can get rid of these minus signs. So, right. So, this is our third relationship. So, third relationship, right, and similarly our Gibbs potential, right, and we wrote it as G equals u minus Ts plus Pv, right, and we can write its differential as du, which is Tds minus Pdv minus Tds minus Sdt plus Pdv plus Vdp, okay, and you can see some terms cancel out simply, and we are left with minus Sdt plus Vdp, right. And again from here we can write our entropy as negative of partial derivative of G with respect to T at constant pressure, volume as partial derivative of G with respect to constant temperature, sorry, with respect to P at constant temperature, and again we can use the property that the order in which we are taking partial derivative of Gibbs potential with respect to its natural variables, which are temperature and pressure, the order does not change. So, I leave it on you. So, if you do that exercise the same way we have done for the three other cases, and we end up with this fourth relationship, which maybe I can write here. So, this is del V by del T at constant pressure equals minus del S by del P at constant temperature, and this is the fourth relationship, and I can maybe very quickly write down all the relationships in one page. So, this is negative of del P by del S at constant V equals del T by del V. This was the first relationship. The second one was del V by del S at constant P equals del T by del P at constant S. The third one was del S by del V at constant T equals del P by del T at constant V. Okay, and these are the 4 set of relationships, and these are known as Maxwell's relations. Okay, so 1, 2, 3, 4. Okay, so this is first, second, third, and fourth. All right. So before we end, we will quickly go through two more very useful definitions, right? Okay, so some more definitions. Okay. So the first one being what's known as expansivity. So what do we mean by expansivity, right? So it basically denotes the fractional change in volume with respect to temperature, right. So that is the definition, right. So and it's typically denoted by a symbol beta, right, and like I said, this is fractional change of volume. So this is 1 by V and with respect to temperature, so this is del V by del T, right. And usually we can do this process in 2 ways, right. So either we can keep the pressure constant, right, and we can evaluate this partial derivative while keeping pressure constant, in which case this is known as isobaric expansivity, right. And if we keep the volume constant, the heat constant, right, if we isolate the system and don't let the system to exchange heat with surroundings, which means the entropy change is constant, right. So this becomes 1 by V del V by del T at constant entropy, and this is known as adiabatic expansivity, right. So either we can do it at constant pressure or we can do it at constant entropy, right, in adiabatic conditions. Okay, so these two definitions, and the second one that we will use is known as compressibility. Okay, and again similarly this is also fractional change in volume, right, and the name suggests its compressibility, right, which means we are compressing our system. So this is with respect to pressure, right, and this is denoted by symbol kappa, right. So kappa, right, and like I said, so this is fractional change. So this is 1 by V del V by del P, right, and now we can do this process at either at constant temperature, in which case this is known as isothermal compressibility, right, and or we can do it at constant entropy, right, and this is 1 by V del V by del P at constant entropy, in which case this is known as adiabatic compressibility. And another important thing here is that as you can now imagine, if we apply pressure to any system, right. So what we are doing is we are basically reducing the volume of the system, right. So therefore by increasing P, the V goes down. Okay. So that naturally gives a negative sign to this quantity, right. So this can never be positive. So usually what we do is we just put a negative sign here so that this quantity becomes positive. Okay. So this is just for our convenience. Okay, so there is a negative sign because V decreases with P. Okay, but that was not the case here, right. So if you increase the temperature of the system, it will expand, right, its volume will increase. So as T increases, V also increases. So we don't this is always positive, right, and to make this compressibility also positive, we put a negative sign. Okay, and the last thing that we will do is which basically will continue in the next class as well. It's known as Joule expansion. So, what is Joule expansion? Okay. So let us consider a situation where we have this gas, right, and we have created a partition such that all the gas molecules, they occupy 1/2 of the container, and this entire system is thermally isolated, right. So, it can't really exchange heat with surroundings, right. And what we do later is we basically remove this wall. Okay. So, same system, now we open this wall, right, and what is going to happen, these molecules will expand into emptiness, right. So, this is again insulated, okay, no heat exchange allowed, and we have opened the partition, right. So, basically Joule expansion is expansion of gas into an empty region, right. Okay. And based upon this, we can define something known as Joule coefficient. Okay, Joule coefficient, which is denoted by symbol mu j, and this is the change in temperature with respect to volume at constant entropy, right. So, what we are interested in is, so we are trying to ask, if my system is doing this process, what happens to the temperature of this process, what happens to the temperature of the system, right. So, I somehow partitioned, or I somehow I moved all the molecules in one corner, and I suddenly remove the wall, right, and these molecules eventually they will like go into the empty area, right. And the question that we are asking is whether there is any change in temperature of the system, right. And we are doing it as a function of volume, because essentially what we are doing is we are increasing the volume of the system, and it happens at constant entropy because we have isolated our system. So, this is an adiabatic process, right. So, this is adiabatic process, and in fact I can write here adiabatic expansion. Okay. Okay. Now, you should be little bit worried, right. So, remember when we are dealing with ideal gas, right. So, all the internal energy in the ideal gas is the contribution comes from the kinetic energy, right. So, so it does not matter what is the volume of the system, right. So, the temperature change has to be 0 because it is isolated, it is not exchanging any heat, right. So, so for with confidence, or okay. So, for an ideal gas, since the temperature does not really depend upon the volume, right, it is the property, this is like the total kinetic energy of all the gas molecules, and it is independent of how far these gas molecules are with respect to each other, right. So, for an ideal gas, the dependence on temperature with volume is 0. So, therefore, this Joule coefficient is 0, right. But what about a real gas? Okay. So, that is what we will basically do in the next class, right, because as you know, we have already used this fact that in real gas, since there are intermolecular attractions, right. So, as we change those interactions, we are changing the internal energy of the system, right. So, for a real gas, internal energy is not only the function of temperature, but also the function of volume, okay, and we will try to see how we can evaluate this Joule coefficient for a real gas, okay, that we will do in the next class.